So quickly, let me just talk about me really quick. I joined Confluent in 2020 after interning in 2019. I worked on Apache Kafka basically since 2019. And some of the KIPs I worked on are KIP-890, the sticky partitioner, the first version, topic identifiers, transaction server-side defense, which is what I'll be talking about today, KIP-1022, which is about formatting and updating features. I became a Kafka committer in 2022 and a PMC member in 2023, and what that means is basically I've been working and reviewing Kafka for many years now. Okay, so let's talk about KIP-890. KIP-890 was designed with two main goals in mind. The first one is that we wanted to address hanging transactions issue on all clusters. I will go over what a hanging transaction is in great detail in a couple slides. And the second thing we wanted to do with this KIP is we wanted to improve the transactional protocol for new clients. So how would we do that? First thing we want to do is improve the performance of part one and to add some correctness improvements to the transactional protocol. Part one was fully released in Apache Kafka 3.7, but there were some aspects in Apache Kafka 3.6. And part two, we're aiming to release in Apache Kafka 4.0, so coming soon. Okay, before I get into the KIP, I want to go over how transactions work, what they are, all the nitty-gritty details. So generally, in Kafka, you may have a use case where you want to write to a bunch of partitions, and you want to write to all of the partitions or none of them at all. So if there's some failure in the middle while you're writing, you want to roll back and potentially start over. So how does that work? Well, transactions were introduced to Kafka with KIP-98, and a high-level idea of how it works is that your producer is going to begin the transaction and start writing to the partitions that it wants to write to. And there is a central coordinator that keeps track of all these partitions. Producer can also commit consumer offsets. Maybe if you're reading from something and doing some processing, you want to commit the offsets that you've read. And the producer then can choose to commit if everything looks good or abort if there was some issue and you need to roll back. Once the producer has made the decision, the coordinator is the one who sends all the markers to the partitions to complete the transaction and either commit it or abort it. Okay, so I want to go into each step a little bit more into detail. And at the bottom of the screen, we're going to have the transaction state log, which is persisting the different steps of the transaction. So if there's a failure and the transaction coordinator dies for whatever reason, we can come back up and continue the transaction. So this first step, when we begin the transaction, we get when we start the producer to write the transaction, we actually provide a unique transactional ID. And when the producer comes up, it will register with the cluster and get a corresponding producer ID. This is assigned by the cluster, and you have a mapping of transactional ID to producer ID. It's a kind of a one-to-one mapping. And this mapping is going to be persisted, so it's going to be in our state log. Each producer can only write to one transaction at a time. So once you start a transaction, you have to complete it before you start a next one. And each transaction only has one producer writing to it. So you can't have two producers writing to the same transaction. However, transactions can contain multiple partitions. So the one producer writing to the one transaction may have multiple partitions. So as I mentioned, we will register with the cluster and we'll persist a mapping. So in our transaction state, we're going to have some sort of record that tells us transaction ID X has producer ID 123, something like that. So the next step is the central coordinator is going to keep track of all the partitions in the transaction. So we're persisting the state of all the producers it's assigned to. And how producers get assigned to the coordinator, it depends on the transactional ID. So when you assign your producer transactional ID, that transactional ID is hashed, and that hash value will correspond to some transaction state partition, and whatever broker is hosting, whatever one is the leader of that partition, will be the coordinator for that producer. The producer will then tell the coordinator to persist the partition. So there'll be this add partitions request that we send to the coordinator, and we'll add our partitions. So for example, foo, that's one of our partitions in our transaction. We're going to add it. And maybe we have another partition like bar. I put these 3 asterisks because for now, the producer has to send this request directly to the coordinator, but that may change with KIP-890. Well, spoiler alert, it will change with KIP-890. So I mentioned earlier the producer can also commit consumer offsets. So besides writing the data, you might want to commit the offsets, and this is useful in those streaming cases where maybe you want to read from some input partition, do some processing operation, and then commit the output. And you only want to do that exactly once. You don't want to reread it and reprocess. The offset partitions that are basically based on the group ID of whatever the group you want to commit offsets for are also persisted in the transactional state. So in this example, I'm showing transaction X has some offset commit for group Y. In the state, it will actually share whatever that consumer offset partition is, but for simplicity of this diagram, we can view it like this. So we're finishing up the transaction, and we're deciding whether we want to commit or abort the transaction. And once we've made this decision and once it's persisted in our state, this will make these, we want to make these either, we either want the records to be visible to the consumers or we want them to be skipped over. That's kind of how the aborting or committing works. If we commit, then all the records in the transaction will be visible, and if we abort, then they won't be. So yeah, aborting keeps the records hidden but advances the log. And the producer will tell the coordinator of their decision. So how this works, producer will say, I want to, let's say, commit our transaction. And we write this prepare marker in our transaction state log. And what this prepare marker does is it includes the information about whether we committed or aborted the transaction. And if the transaction coordinator were to fail at this point, we would persist that original decision. It might have been confusing when I said it earlier. Writing this specific marker doesn't make it visible yet, but what makes it visible to the consumers is sending the markers to the partition. So the coordinator, once it gets its decision from the producer, will send commit or abort markers, depending on their decision, to all the partitions it had been keeping track of. So in this case, we have the foo, we have the bar, and we have the consumer offsets partition. And once all of the partitions have received their markers and written them to their log, we will complete the entire transactional state with the complete record. And so there we go. There's our complete transaction. Once the partitions have their markers written to them, they're available to be read by the consumers if it was a commit. So let's go a little bit deeper into reading the transactional data. The non-read committed consumers are non-transactional consumers, and they're just going to read up to the high water mark. For a little bit more explanation of what high water mark is, it's just the offset that all of the in-sync replicas are replicated to. So when you have a normal producer, your producer will write to the leader and it will replicate to its followers. And as long as the followers are all in sync, your high water mark will keep advancing as you replicate. But for transactions, we have a special consumer. It's called the read committed consumer. And it doesn't read up to the high water mark. Instead, it reads up to the last stable offset, the LSO. And what is the LSO? The last stable offset is the minimum of the high water mark and the first non-committed offset in the log. So we know what the high water mark is. What is the first non-committed offset in the log? This is basically the first record or offset in our partition that is part of an active transaction. It's not been completed. So as you scan through the log, as soon as you encounter an offset that is part of a transaction that is not complete, that is your LSO. You cannot read past that point. So let's look at an example. So let's say we start a transaction with producer ID 2. At this point, our LSO is exactly at this offset. We have an open transaction and we can't read it. And let's say we keep writing and then we commit it. At this point, our LSO has updated. It's essentially the same as the high water mark because let's say all of our replicas are replicated to this point. And we can read this data now of this transaction with producer ID 2. If we start a new transaction, our LSO will update, and maybe we could start a new transaction with a different producer. We can interleave them. There's no requirement that we can't. We keep writing, and maybe we made the decision to abort this producer ID 2 transaction. At this point, the LSO is not going to update to the abort marker because we still have an open, uncommitted transaction with producer ID 5. So at this point, you could read up to this 2 of the producer ID 2, but anything past that is past the last stable offset, and we can't read it. And you could imagine we keep going, and if we committed that transaction with producer ID 5, the LSO will update to now this new transaction with producer ID 7. It's the first uncommitted, non-committed offset in the log. So what does the consumer see, right? We talked about where the LSO is, but that's not the whole story. So let's consider this previous example. Some of the records with producer ID 2 were committed and should be viewed, but others are not. And we know that any given record contains a producer ID, a sequence, and an epoch. Let's go over what those are really quickly. So the producer ID, we talked about it earlier. It's the unique ID that the cluster gives the producer to identify records written by that producer. Sequence is used for the idempotent producer to make sure that the records are in order and there aren't any duplicates. And an epoch is a monotonically increasing number used to fence previous instances or any errors that you may encounter. So, for example, maybe you have a producer that comes up, it starts with epoch 0, and you have a new producer with the same transactional ID that you bring up. You don't want to have 2 of these producers up at the same time because you could get inconsistent information. So the new one that comes up will have epoch 1, and it will fence the old one. And if the old one tries to write, it will fail because the epoch is too low. Similarly, if there's some sort of error that's irrecoverable, we want to fence any zombies or any other requests that might come in after that error, so we'll bump the epoch on that error. So we have this producer ID, we have the sequence, and we have an epoch, but we can't actually tell the decision about the transaction from the record itself. And why is that? Even though we have this producer ID and epoch, transactions can share epochs. So what this means is that you can't uniquely identify a transaction with just the producer ID and epoch at this point in time. You could have one with producer ID 2 and epoch 0 that commits and one that aborts. So instead, what we do in Kafka is that we actually keep a data structure containing producer ID and the first offset of an aborted transaction. And when the consumer gets this information, it'll actually sequentially go through the log, and as soon as it encounters that producer ID within that offset range and it hasn't seen an abort marker yet, it'll skip that data. So let's kind of go through it, right? If the consumer tried to fetch this information, we would get the aborted transaction. I didn't put an offset, but we can say it's at 2 for this producer ID 2. So as we're going through, this first offset is not 2 yet, so we can read it. This one is good. But we see this one was producer ID 2 at the 2, and we haven't seen the corresponding abort marker yet, so we can't read it yet. This one we can read, it's the producer ID 5. We don't have any information about producer 5 being aborted. And this one is also producer ID 2, and once we encounter the abort marker, we can say, okay, no more aborted for producer ID 2, and yeah, that's how that would work. Okay, so I talked a little bit about how important the LSO is for consumers when they're reading read committed data. So what happens when the LSO never advances? So consumers can't consume past the LSO, and we also can't compact topics past the LSO. And so what this means basically is we kind of get stuck. We get stuck trying to process our partition. If there's any transaction in that partition that had an issue, you can't read anything else in the partition. You can't compact anything else in that partition. So your processing might stop and your disk might fill up because you're not able to compact. And one common cause of the stuck LSO is something we call a hanging transaction. So in this example, we're writing all this data, but we never closed the transaction with producer ID 2, so that LSO is stuck. Okay, I've talked about it a lot, so let's go into the details about what a hanging transaction actually is. But before I do that, I want to say what it is not. So there's a common misconception with hanging transactions that a hanging transaction is simply a transaction that a producer never aborted. Maybe a producer started a transaction and then died, and it just never got to make that abort or commit call. But the thing about Kafka is that there is a configuration called transaction timeout MS, and that defines the maximum length of a particular transaction, how long it can be open. So when we hit this transaction timeout MS, the server will actually automatically abort any open transaction that has exceeded the time that it specified. And at this point, we also fence the producer. So the thing I mentioned earlier about bumping an epoch, at this point, we'll bump the epoch, and if that producer somehow comes back and tries to do anything, it will be unable to because it's fenced. And that LSO will update because we write the abort marker, and we'll be able to continue on with that partition, doing any more writes or any more reads we need to do. So we know that if the coordinator knows about this this transaction that's open, it will automatically abort it. But what would happen if the coordinator, for whatever reason, didn't know that there was a transactional record written on a partition? That is what we consider a hanging transaction for today. So when the coordinator doesn't know, it's not able to periodically check if we've elapsed this transaction timeout, and we will never abort it, and that LSO will never update. Well, how does this happen, right? There's a few ways this can happen, but it kind of falls into maybe two buckets. One is race conditions, and maybe client bugs. So let's zoom in a little bit more on kind of this race condition that I mentioned. So prior to KIP-890, we didn't have any way to ensure a transaction was ongoing when writing. So we have that add partitions call. We add the partition to the transaction. The coordinator knows about it. And then we have a separate call to produce to that topic. And that produce call doesn't check anything. It just says, OK, I'm producing to this partition. Hopefully the coordinator knows. But there are some edge cases with this. And a produce message can actually come in after a marker, so after a commit or after an abort marker. And we've typically seen this sort of issue when there's maybe a network connectivity issue, maybe a disconnection, and the TCP retransmit is trying to repeatedly write this message. And even though bumping an epoch fences older epochs, there are some cases where we're not bumping epoch on a transaction. So this message that comes in late is not fenced. So as a little example, we start our transaction with producer ID 2. We're writing. And maybe we encounter some network issue or some issue where this record didn't get written. And then the client decides to maybe abort the transaction. And then, this message comes in late, and it's coming in after this marker, and the coordinator didn't know about it. This is the case we were talking about with the hanging transaction. There's also another similar case that can happen if we try to continue writing with this producer. And basically what can happen is the message that was meant for the previous transaction will join the next one. And the decision that was made for the previous transaction doesn't necessarily apply to the new one. So, if we'd already added, we can keep writing with this producer, and we might end up committing this record 2 that maybe wasn't meant to be committed at all. So that's pretty bad, right? We want to fix this hanging transaction issue, and we want to fix any of these gaps in the transactional protocol. But one thing to keep in mind when fixing issues in Kafka is updating something on the server versus updating something on the client. There's kind of different timelines for these different updates. So typically on the server, we update that more frequently. Usually the server is kind of a more central within a business or within someone who's running Kafka. And the clients are maybe run by different people and they're maybe not updated on the same cadence. But we want to fix this hanging transaction as soon as possible. It's causing all these issues. We're not able to read. We're not able to compact. How can we fix this quickly? So one way to fix this quickly is to focus on just trying to fix it on the server side and getting that fixed out first. And this would mean that we can fix hanging transactions on old clients, right? So that's what all KIP-890 Part 1 is about. We want to eliminate hanging transactions on old clients by simply making the fix on the server side. So what we're going to do is we're going to add a check on the server side to verify with the coordinator that the partition has been added. So we'll do the add partitions call, and on the produce request, we will send another message to the coordinator just confirming that it was actually added to the transaction before we write to the partition itself. And this requires an extra hop, or the request to the coordinator. So it's going to be maybe a little bit slower than before. So in this example again, we start writing, we check if it's been added. In this case it was, everything's good. And once we've checked once for a partition, we can keep writing to it. And we have this fault again, and we're not able to write this record. And then, we abort it again. And then this time, we try to write the record, we check, and because this is this retransmitted record, we didn't actually add it to the partition, or add the partition to the transaction yet, we will reject it, and it will get sent away. It will not be added to the transaction, and we won't have a hanging transaction. So cool, that's awesome, that's exactly what we wanted. Now, there is one small caveat with KIP-890 Part 1, and that is if for some reason we were about to write another transaction with producer ID 2, there is a small chance that maybe we've added this partition of the next transaction already. And in this case, it could still join. It would be super rare, but there is a small chance that we do rewrite the wrong record to the wrong transaction. So we do want to fix that, hopefully with KIP-890 Part 2. So let's quickly go over how to enable KIP-890 Part 1 before we get over to KIP-890 Part 2. So the way you enable it is setting this transaction partition verification enable to true. This is the default in the versions that it was introduced in, but for whatever reason, if it gets unset, this is how to set it. In AK 3.6, all of the data partitions are verified, and in 3.7, we are also verifying the offset commits. This configuration is also a dynamic configuration, so for whatever reason, if you need to enable and disable it without restarting all your cluster, you can run this command. And one really interesting thing is before we rolled this out to our production, we saw about 5 hanging transactions per week when running in the cloud. And after we rolled it out, we've essentially seen 0 hanging transactions per week. So super, super great result there. Really happy with that. All right, let's get over to KIP-890 Part 2. So, we said earlier that there was a potential performance issue and, not issue, but performance regression. And we also saw that there were some correctness issues with the first solution. So how do we fix those? So one thing that's kind of a no-brainer is we should just bump the epoch on every transaction to fence any late messages that might try to come in. In the case that we saw before, we won't ever see that late message come in because the epoch will be the previous epoch, and we won't write any message of the previous transaction to our next transaction. The other thing we wanted to do was help with the performance. So we can eliminate that extra hop and the client requirement by adding the partition in produce. So rather than sending an add partitions sending a produce request, and then sending a verification request. We can just send a produce request and add partitions request and use that kind of same logic to make sure that it's been added when we write. For this, though, we need to update both the client and the server to handle these two new use cases. So now, if we look at our example, I'm going to include the epoch in the records as well. So this first transaction will be epoch 0. We see our fault. And then when we abort, we're going to bump that epoch so now it's 1. And then when that second, that late message comes in and it has epoch 0, it's fenced. It's not able to get to the partition because it's the last epoch. And we will correctly write the records we want to write to this transaction to the transaction and commit it. So how do we, questions at the end, sorry. Yeah, sorry, thank you. So how do we enable part 2? Requirements here are 4.0 producer client and transaction version 2. Transaction version is something new introduced by this KIP. It's also part of KIP-890 that I mentioned as my About Me slides. It's similar to metadata version, but is used to control transaction features specifically and will be new to 4.0. So for new clusters, if you want to enable this feature, you just need to make sure when you're formatting your cluster using the storage tool to also set the feature version to transaction version 2. And if you're running an existing cluster, you just need to use this upgrade command. One thing about 4.0 is that we're craft only at 4.0, so all of these requirements are for craft clusters. Yeah, so coming soon to 4.0, maybe a little bit fingers crossed, but that's the plan. So I just want to go over kind of the upgrade path, just to really solidify how this will work. Once we get 4.0 released, we will start maybe running a cluster with 4.0. Maybe we upgraded it to 4.0 and everything is transaction version 0. And for part 1 with verification, the way it works is first we add the partition to the transaction, then we produce, we do a verification, and then once everything is good, the produce response will reply that it was correctly written and it was acknowledged. But when we upgrade, we're going to use this features tool. We'll upgrade to version 2, and that will dynamically get updated on all the brokers. There's a API versions request that sends information to the client about the different API versions that are supported, as well as the different features that are supported. So once the client sees that the cluster supports transaction version 2, it can start using the KIP-890 part 2. And whenever we send a produce request, we'll just simply send the produce and add partitions. There's only 2 requests here, and the client only needs to send 1 request. So once we've written the record, we will return the response. So one other thing I wanted to cover briefly today is a very similar issue, but is actually quite different from hanging transactions, which is Kafka 16.352. This issue is similar in the sense that you cannot read past this transaction that has an issue, but rather than the issue being that the coordinator doesn't know about the transaction, it's actually a transaction that gets stuck trying to commit. And so what happens is we have a transaction that has a decision. In this case, let's say it was commit, and we've written the prepare marker. When we write the prepare marker, we send the end transaction request to all the partitions that were part of the transaction. So in this case, foo, bar, and the consumer offsets partition. And there's also a coordinator epoch associated with this request. And that's based on when the transaction coordinator was a leader or was reloaded. And so when we send this request, we have a pending state that should be, when the response comes, the pending state is transitioned to the actual state, and we'll write the complete message in the log. So let's say we send out this request. Now, there are a few ways that the transaction coordinator can reload while it is still running. And in that case, we will bump the coordinator epoch. Some of those cases are, if ISR changes happen. There's a few other cases. So here we reload, and we're sending out that same request because we see that the transaction is ready to be committed. That's the next step. But now we have the request with the coordinator epoch 1. So it's not necessarily a bad thing. We're just sending 2 requests with the same information. It's still the same decision, so there's no change. The transaction result should be the same. But the problem here is that when this first request comes in, it will clear the pending state, but because the epoch is the old epoch, we won't actually write the record. So that's pretty bad. We'll get stuck in this state where we're not able to complete the transaction until we restart the broker. But the good news is that this issue has actually, so the request will come in and it won't be able to do anything because there's no pending state. The good news is, though, that we fixed this issue. And the way we fix this issue is pretty simple. Now in our pending state, we're just going to include an epoch. And so in the case where we reload, we just need to update that epoch to be the newest epoch. And so when we get the stale response, we just ignore it because it's the old epoch. And when we get the correct response, the latest epoch response, we can write that complete marker. And the transaction state is complete, and the producer can start a new transaction, and everything will continue as normal. Okay, so I want to talk about a few future-looking plans. There are some KIPs in the works and some other ideas that build upon KIP-890. Specifically, the epoch bump on every transaction is really important for some of the future projects. And one of those future projects is atomic dual rate recipes with Kafka two-phase commit, KIP-939. And Artem, he's actually here. Hi, Artem. He'll be speaking about that tomorrow in Ballroom E, which is this room, at 4 p.m. So if you want to learn more about that, I recommend you come back and listen to his talk. Okay, that's it for me. I've included the link to the KIP if anyone is interested, and I think we should have some time for some questions. So that's it. Thank you.